3IATLAS woke up 16 AU from the sun, billions of miles too early. A sleep documentary script. Part 1, the question that shouldn't exist. Something turned on in the darkness where nothing should be awake. 16 astronomical units from the sun, in a region of space so cold and distant that even water ice stays frozen solid, 3IATLAS began to glow. Not the faint reflected sunlight you'd expect from a dormant chunk of rock and ice, but an active, measurable emission of gas and dust. Carbon monoxide jets erupting into the void, a coma forming around the nucleus. Before we dive any deeper into this mystery, I just want to say something real quick. Making these documentaries, it's a ton of work. Days spent digging into research, writing scripts, editing, trying to share stories that are both accurate and actually interesting. If you like what I do, if these stories about the unknown get your brain buzzing, I'd really appreciate it if you subscribed or left a like. It's not just about numbers. It tells me this stuff matters, that we're all curious together. Thanks for being here. 3IATLAS woke up 16 AU from the sun, billions of miles too early. A sleep documentary script. Part 1, the question that shouldn't exist. This is about something stranger, the moment when science, with all its careful models and well-tested math, runs into something that just won't play by the rules. When observatories across the US and around the globe started picking up activity from 3IATLAS at distances where nothing should be happening, astronomers didn't freak out. They double-checked their data, ran through their calculations again, looked for mistakes, but the same impossible result kept popping up. The discovery didn't come with any grand announcement. It crept in quietly, just a growing unease among astronomers. At NASA's Jet Propulsion Lab, at telescopes in the Southwest, in university labs where grad students stared at spectral data late into the night, everyone started to notice the same weird thing. This comet, a visitor from another star system, was acting in ways that didn't fit anything we thought we knew about how comets behave. Let's talk about what 16 astronomical units really means. 1 AU is the distance from Earth to the Sun, about 93 million miles. 16 times that is nearly 1.5 billion miles from the Sun. Out there, sunlight barely whispers across the darkness. Each square meter gets only a sliver of the energy we feel on Earth. At that distance, water ice doesn't turn to gas. It just can't. There's nowhere near enough heat. The physics is rock solid, backed up by thousands of comet observations. So picture yourself standing on 3IATLAS, 16 AU from the Sun. The Sun isn't a blazing disk anymore. It's just a small, intense point. The solar wind, that constant stream of charged particles, is barely a breeze. The temperature, around -200 degrees Celsius or -320 Fahrenheit. That's so cold, carbon dioxide freezes solid. Nothing liquid can survive. Only the most volatile stuff can even try to go from solid to gas out here, and even then it's a stretch. But 3IATLAS just shrugged off those rules. Then the Atacama Large Millimeter Array, 66 radio dishes out in the Chilean desert, some of the most sensitive gear on Earth for picking up faint signals from faraway objects, turned its sights on this comet. What they found shouldn't have been possible: carbon monoxide. Not a faint hint, not some fuzzy maybe signal you could blame on noise or equipment quirks. Real, clear spectral lines showing carbon monoxide gas venting straight out from the comet's nucleus. The evidence stood out. Multiple observations confirmed it. Other teams checked and checked again. This wasn't some glitch. The data was real and the comet was breaking the rules. Let's pull back for a second. Normally, comets are pretty predictable. In our solar system, they hang out in the frozen outskirts, places like the Kuiper Belt or Oort Cloud, made of ice and rock, leftovers from way back when the solar system formed. Most of the time, they're asleep, frozen, quiet, drifting through space on their long, lonely paths. Out at the edge of the solar system, you find the Kuiper Belt, and way beyond that, the Oort Cloud. These places are like deep freezers for the leftovers of planet formation. It's unbelievably cold, just a notch above absolute zero. Nothing stirs, nothing changes. Everything just sits, frozen in time. Most of these icy bodies will never move undisturbed for billions of years. But every so often, gravity or a wandering star gives one a shove, and it starts a slow, long tumble toward the sun. When a comet finally gets closer, things wake up fast. As it crosses the frost line, a sort of invisible boundary where sunlight finally gets strong enough to turn ice straight into gas, the show begins. Water ice starts to vaporize. Gas and dust burst out of the comet's hard core. A glowing coma forms, wrapping the nucleus in a fuzzy halo. Sometimes, if conditions line up, a tail appears, streaming millions of miles into space as the sun's wind and light push the debris away. This isn't new. Astronomers have watched it unfold for centuries. We've got math that nails down when and where a comet will spring to life, all depending on how close it gets to the sun. For most comets, where water is the main ice, nothing much happens until they cross inside about 5 astronomical units, that's around Jupiter's orbit. Get to 3 AU near Mars and activity ramps up. By 1 AU, Earth's spot, they're roaring, spewing gas and dust at rates we can measure and predict. These models work. We've checked them against hundreds of comets, long-period ones from the Oort cloud, short-period travelers from the Kuiper belt, the regulars that swing by every few years. They all follow the rules. As they approach the sun, they get brighter just as the math says they should. Gas pours off in amounts that match the physics. The tails behave in ways that fit what we know about solar wind and light. It's solid science, reliable, tested, and usually right. Then along came 3IATLAS. Astronomers spotted it outgassing at 16 AU, way past where water ice should even think about becoming active. That's out beyond Saturn, in a place so cold even carbon dioxide can't really sublimate enough to explain what we were seeing. Only a handful of materials can evaporate out there, what scientists call supervolatiles. Stuff like carbon monoxide, nitrogen, methane. These ices form at extremely low temperatures and can turn to gas even in the deep freeze of the outer solar system. But most comets don't have much of these, or if they do, those volatiles are buried under more stable ices like water and CO2. Usually they just don't run the show, especially not so far from the sun. But that's exactly what was happening with 3IATLAS. The spectra told the story. Carbon monoxide was pouring out, not water, not carbon dioxide. And it wasn't just a little bit. It was a strong, steady blast, way more than you'd expect from a thin surface patch. It looked like the comet's core was loaded with supervolatiles, venting gas billions of miles from the sun. The numbers backed it up. By measuring the intensity of the carbon monoxide spectral lines, scientists could figure out how much was escaping every second. The answer, a lot. Enough to mean either the comet had a wildly active surface or a huge area of exposed supervolatile ice. Either way, it didn't fit the playbook. American astronomers, especially those using NASA's telescopes and big ground observatories, were among the first to spot that something weird was going on. The usual comet models just didn't work. Follow-up observations from Arizona, Hawaii, Texas, you name it, confirmed the oddity. Then teams in Chile, Europe, and other places joined in. No matter who looked, the story was the same. 3IATLAS was active in a place where comets are supposed to sleep, venting gases that usually stay hidden, and doing it all with a force nobody had seen at such a distance. This stirred up a whole mess of questions, ones that don't come with easy answers. Scientists are still wrestling with them, honestly. They hit right at the core of what we think we know, how comets actually work, what happens to stuff as it drifts through interstellar space for millions or even billions of years, and what these cosmic wanderers really tell us about how planets form around other stars. Even spotting 3IATLAS was a big deal. Interstellar objects, chunks of rock or ice that come from other star systems, are almost never caught passing through our own. At least that's what our records showed. The first one we ever confirmed, 1I/Oumuamua, only showed up in 2017. People went wild over that thing. It was long and spinning, and it sped up in ways gravity couldn't explain. Some scientists said it was outgassing, while others threw out way stranger theories. Then in 2019, we found 2I/Borisov. That one looked and acted more like a normal comet, which seemed to quiet down the more out there ideas. Jump to 2024 and there's 3IATLAS. Another interstellar comet, at least that's what it looked like. Its path was hyperbolic, so it wasn't stuck to the sun the way our regular comets are, just passing through. Early on, it showed off a coma and started behaving like a typical comet. Scientists figured they knew how this would go. It'd stay quiet out past the planets, then, as it got closer to the sun, it would heat up, get more active, peak at perihelion, and then fade as it left the solar system behind. But 3IATLAS didn't stick to the plan. It started waking up way sooner than anyone expected, at 16 astronomical units out, no less. That changed everything. Suddenly, people had to rethink what this object was all about, and what it could actually reveal about the universe outside our solar system. Let's clear up what waking up even means here. We're not talking about the comet being aware or anything like that. It's just physics. When we say it woke up, we mean it went from being a frozen, silent hunk of rock and ice, barely reflecting sunlight, basically invisible, to spewing gas and dust into space, building a coma you could spot with a telescope. Here, what's happening? Sunlight hits the comet, the surface starts to warm up. If it gets hot enough, the ices inside start to sublimate. Basically, they turn straight into gas. Pressure builds up under the surface until it finds a crack or hole to escape through. When the gas bursts out, it drags dust along, and that's how you get that glowing coma and tail. But at 16 AU, that's a different story. The sunlight out there is about 250 times weaker than what we get on Earth. Imagine standing outside on a bright summer day, feeling the sun on your face. Now cut that warmth down to less than 0.5% of what you're used to. That's what 3IATLAS was dealing with when it started releasing carbon monoxide. So how does that even happen? A few things could be true. Maybe 3IATLAS is loaded with supervolatile ices that don't need much heat to turn to gas. Or maybe those ices are right at the surface, not buried under tougher stuff. It's possible there's another heat source inside, radioactive decay, leftover heat from when the thing formed, or something we haven't figured out yet. Or maybe, and this is the wildest idea, drifting through interstellar space changed the comet in a way that makes it behave differently. Each of these explanations points in a different direction. All of them matter for how we understand comets, how planetary systems form, what's floating around between the stars, and just how weird and varied these small bodies can be. And honestly, every answer comes with its own pile of new questions. So if the nucleus is loaded with supervolatiles, what's going on? Most comets in our solar system aren't like that. They're mostly water ice, with just a bit of carbon dioxide and some other stuff mixed in. So, running into a comet from another star system that's made of something totally different hints that the conditions where it was born were nothing like what we see here. That actually makes sense. Different star systems can be wildly different. But it also means we can't just assume our solar system's comets are typical for the whole galaxy. Every interstellar visitor could bring something unexpected, something that just doesn't fit the categories we've built from our local examples. Now, if the nucleus is built in a way that makes its volatiles easy to reach, that opens up a whole new set of questions. How did this comet form? How did it survive out there for so long? Comets are fragile. People call them dirty snowballs for a reason. They're just loose mixtures of ice and dust, barely held together. If 3IATLAS has a structure that lets its deep volatiles escape easily, maybe it's also more likely to break apart or erode. Yet somehow, it's still in one piece after possibly millions or even billions of years drifting through the harshness of interstellar space. And if there's some kind of heat source inside the comet, things get even weirder. Radioactive decay is one idea. Some isotopes like those of aluminum, potassium, or thorium can give off heat. But you'd need a lot of them, and if we could check the isotopes, we'd expect to see signs of that. As for leftover heat from when the comet first formed, that seems pretty doubtful. After millions of years in deep space, any original warmth should have disappeared long ago. That brings us to another idea. Maybe 3IATLAS changed during its trip between the stars. This is where things get really interesting, and honestly, a little unsettling. If the long journey through space can actually change what a comet is made of, or how it acts, then every interstellar object we find isn't just a time capsule from another solar system. It's something new, something reshaped by forces and events that play out over distances and timescales we're only starting to grasp. Take galactic cosmic rays, for example. These high-energy particles fill the space between stars and bombard anything out there. Over millions of years, they can work their way into a comet's surface, breaking chemical bonds and building new molecules. Simple stuff like carbon monoxide and water can turn into more complex organic compounds. New types of ice can form. The whole texture and porosity of the comet can change. Scientists have modeled this cosmic ray processing and even mimicked it in labs, but we've never really seen what it does to an actual object that's spent ages out in deep space. If 3IATLAS got a heavy dose of cosmic rays on its journey, the outer layers of its nucleus could be completely reworked by radiation. That actually fits what we see. The coma's strange carbon dioxide to water ratio. Cosmic rays can slowly turn carbon monoxide-rich ices into carbon dioxide. The odd activity far from the sun. That could come from a surface that's been changed so much that it now lets volatiles escape more easily. Lately, teams using data from American observatories and NASA have started digging into this idea. They've run computer models showing that when comet-like materials get blasted by cosmic rays for millions of years, big chemical and physical changes don't just happen, they're pretty much guaranteed. So it's not really a question of whether interstellar objects get processed as they travel. They do. The real questions are, how much did they change, and exactly what new traits did those changes create? This all matters because it means we can't just look at 3IATLAS and think, so that's what comets are like in other star systems. What we're seeing is the end product of a long, strange transformation. It's like trying to figure out what a glacier looked like back when it formed by studying the pile of debris it left after melting. The clues are there, but they're mixed up, changed, and tangled with everything that's happened since the beginning. And this is where the mystery deepens. Because if we accept that cosmic ray processing can explain the unusual composition and early activity of 3IATLAS, we still have to reckon with the intensity and timing of that activity. Models of supervolatile sublimation at large distances suggest that even with a carbon monoxide-rich nucleus, the outgassing rates detected at 16 AU are at the high end of what should be possible with solar heating alone. The jets were strong enough to be detected by ALMA, strong enough to create a measurable coma, strong enough that some observations reported dust emission along with the gas. That level of activity implies either an extremely active surface or an unusually efficient mechanism for sublimation. And here's where the observations become particularly interesting. The activity appears to have varied over time. Early detections showed moderate emission. Later observations, as the comet continued inward toward the sun, showed increased activity, which is expected, but also fluctuations and possible jet structures that changed between observation periods. Comets can exhibit variable activity due to rotation. As the nucleus spins, different regions face the sun at different times. If volatiles are concentrated in certain areas, you'd see jets that turn on and off as those areas rotate in and out of sunlight. This is well documented for many comets, but for 3IATLAS, the variability seemed more complex. Some observers reported asymmetries in the coma, suggesting multiple active regions. Others noted that the brightness of the coma didn't always follow a smooth curve, as you'd expect from simple solar heating. These details matter because they hint at a nucleus that isn't uniform. It has structure. It has active and inactive regions. It might have layers of different materials or pockets of volatiles that vent suddenly when pressure builds up. All of this is consistent with a natural comet, but a very unusual one. A comet that doesn't fit neatly into the categories we've built from studying solar system objects. So here we are, at the beginning of this story, standing at the edge of what we know and staring into the uncertainty beyond. 3IATLAS woke up 16 AU from the Sun, billions of miles too early by conventional understanding. It released carbon monoxide with an intensity that challenges our models. It showed activity patterns that suggest a complex, structured nucleus. And it did all of this while being an interstellar traveler, an object from another star system that spent an unknowable amount of time journeying through the void before arriving in our neighborhood. The questions it raises are not easily answered. They touch on fundamental aspects of planetary science, astrophysics, and our understanding of the processes that shape small bodies in the galaxy. They force us to confront the limits of models built primarily on observations of objects that formed in our own solar system. They remind us that the universe is larger, more diverse, and more surprising than we often give it credit for. This is not a story with a neat conclusion. It's a story that's still unfolding, still being written by the patient accumulation of observations, the careful analysis of data, and the slow, methodical work of science trying to make sense of something that doesn't quite fit. Over the next sections, we'll explore what scientists observed as 3IATLAS continued its journey through the solar system. We'll look at the data in more detail, examine the hypotheses that have been proposed, and consider what this strange, early awakening might mean for our understanding of the cosmos. But for now, let's sit with the central mystery, something turned on in the darkness where nothing should be awake, and we still don't fully understand why. Part 2, the expected discovery. There's a rhythm to how astronomers find comets, a routine that's been fine-tuned over decades. It starts with big survey telescopes sweeping the sky every night, snapping images of stars and galaxies by the thousands. Algorithms then get to work, comparing each new shot with older ones, scanning for anything that's moved, asteroids, comets, stray rocks, anything that isn't nailed down against that steady background of distant stars. When something pops up, real people step in. Astronomers look at the data, crunch the numbers, figure out orbits, and check if the object's a fresh discovery or just an old friend showing up again. In July 2024, the ATLAS survey, a network of telescopes run by the University of Hawaii and funded by NASA, spotted a faint smudge moving through the sky. This happened at the ATLAS site in Chile, one of 4 telescopes in the system, all of them constantly scanning both hemispheres for anything new. At first, the detection didn't stand out, just another blip on a long list of objects needing a second look. ATLAS itself is pretty impressive. 4 telescopes spread out across the globe, all talking to each other and watching the sky nonstop. Every night, each one stares at the same patch of sky over and over, hunting for anything on the move. Its software does the heavy lifting, tossing out cosmic rays, satellites, and other stuff that just pretends to be interesting. What's left, the real candidates, gets handed off to humans for a closer look. That July night, the system flagged object after object. Most were old news, asteroids with orbits already mapped. A handful were new, tiny rocks lurking in the inner solar system. But then came this one, fainter than the rest, moving in a way that just didn't fit. Once astronomers ran the numbers, they realized they'd found something different. The orbit wasn't a regular ellipse like most comets or asteroids that loop around the sun. It was hyperbolic, an open path, moving fast enough that the sun's gravity couldn't hold on to it. This thing was just passing through, straight out of interstellar space. Only the 3rd time anyone's caught something like this, after Oumuamua in 2017 and Borisov in 2019. The name said it all, 3IATLAS. 3I for third interstellar object, Atlas for the team that found it. Suddenly, every observatory wanted in. This wasn't just another comet. It was a messenger from another solar system, carrying clues from some distant part of the galaxy no spacecraft could ever hope to reach. The buzz was instant, but a little more measured this time. Astronomers had learned their lesson with Oumuamua. That one sent the internet into overdrive, spawning wild theories about everything from alien tech to bizarre chunks of hydrogen ice. Some of those ideas were worth considering. Others were pure science fiction. The takeaway: interstellar visitors always stir up excitement, and sometimes that excitement gets in the way of real science. American research teams jumped on the data. NASA's Jet Propulsion Lab in Pasadena started refining the object's path, predicting where it would go next. Observatories from New Mexico and Hawaii to Arizona and Texas began lining up their telescopes. International partners joined the hunt, pooling observations from Chile, Spain, and beyond. Everyone wanted a piece of this rare, cosmic traveler. Pulling off these campaigns takes serious coordination. Telescope time, that's gold. Big observatories like Keck or the Very Large Telescope are swamped with requests, way more proposals than nights to go around. If you want a shot at using them, you have to write a long, detailed proposal, turn it in months ahead, and hope you stand out among dozens or even hundreds of other scientists with the same idea. But 3IATLAS changed the usual script. The committees in charge of time allocation moved quickly. They kicked in special rapid response programs meant for surprises and fleeting events. Early on, everything followed the playbook. Spectroscopy showed 3IATLAS had a coma, a hazy cloud of gas and dust that marks an active comet. Figuring out the size of the nucleus was tricky. Estimates ranged from a few hundred meters up to several kilometers, but the core was buried inside the coma, and teasing apart the light from the solid center versus the glowing gas and dust meant making a lot of guesses about what the comet was made of and how much light it reflected. Photometry tracked how bright the comet got over time. As it got closer to the sun, it was supposed to brighten. More sunlight, more ices turning to gas, more activity. Astrometry nailed down its exact position, letting astronomers tighten up the orbital calculations and predict its path through the solar system with surprising precision. This kind of observing is all nuts and bolts work. You point the telescope, gather light, sometimes for hours, then go through the grind of calibrating out instrument quirks and the atmosphere's messiness. You pull out the numbers, brightness, position, spectral lines. You check against last week's data. You run the models. Gradually, the story comes together. At first, nothing looked strange. Everything matched expectations. 3IATLAS seemed like another Borisov, an interstellar visitor that, aside from its origin, acted a lot like the comets we already know. Scientists mapped out their plans, what wavelengths to use, which instruments to book, and when to catch the comet at its most interesting points in its orbit. The plan was simple enough. Watch the comet as it neared perihelion, the closest approach to the Sun, set for late October 2024 at about 1.4 astronomical units, just inside Mars's orbit. That's close enough for the Sun to really heat things up, but not so close that the glare would drown it out. Around that time, they expected the action to peak. Water ice boiling off, the coma swelling, maybe even a dust tail forming that ground-based telescopes could spot. After perihelion, the comet would swing back out, passing Earth in mid-December 2024 at about 270 million kilometers away. That's a great chance for close-up study as it speeds back toward interstellar space. Then over the next few months it would fade, moving away from both the Sun and Earth until it finally slipped out of sight. The whole window for observing, maybe a year, start to finish, from discovery to the moment the comet vanished from our view. Getting telescope time isn't easy. Teams had to jump through all the usual hoops, submit a detailed scientific case, lay out why their project mattered, what questions they wanted to answer, and why they needed this instrument at this time. Review panels read the proposals, score them, and pick the winners. The rest try again next time. For 3IATLAS, proposals sailed through at several observatories. The James Webb Space Telescope got on the schedule, ready to scan the comet and break down the chemicals in its gas and dust. Webb's infrared eyes could pick up molecules like water, carbon dioxide, carbon monoxide, and all sorts of organics, building a detailed chemical map. Hubble, still kicking after all these years, would snap images of the coma and nucleus, searching for jets, structure, or signs the comet was breaking up. Ground-based observatories got in on the action too. The Keck telescopes in Hawaii, some of the biggest optical telescopes out there, jumped in to grab high-ray spectra and sharp images. Gemini's twin telescopes, one in Hawaii, the other in Chile, tracked the comet from both hemispheres, so no matter where it was in the sky, someone was watching. Smaller university and research telescopes filled in the gaps, keeping an eye out for any sudden flares or bright spots that might mean the comet was up to something strange. An outburst, a surprise, whatever. The professional astronomy world was buzzing, but you could feel the caution in the air. Sure, this was only the third interstellar object ever confirmed, which made it a pretty big deal. Still, everyone remembered what happened with Oumuamua. That first visitor had acted weird, speeding up in ways nobody expected, and the theories got out of control fast. Some folks threw out wild ideas about alien light sails or weird hydrogen icebergs. Others tried to make the numbers work with regular old comet outgassing, stretching the models every which way. Nobody wanted that circus again. So this time, with 3IATLAS, the community decided to play it safe. Watch first, collect good data, analyze it carefully, and keep wild speculation in check until the evidence really demanded it. Publish only after the work survived tough peer review. Don't jump to wild conclusions or feed the hype. Protect the credibility of the field by sticking to what the data could actually support. That's how science is supposed to go, especially when the public is watching and rumors can spread way faster than facts. You stick to the evidence. You test your ideas. When the facts don't line up, you go back and rethink things. You're honest about what you know for sure, what's likely, and what's just a guess. The whole system of scientific publishing encourages this cautious approach. Submitting a paper means running a gauntlet. Anonymous experts tear through your arguments, hunt for mistakes, ask for more proof, and point out anything you missed. They might ask for big rewrites, more data, or sometimes just say no and reject the whole thing. It's a slow, sometimes painful process, but it's how bad science and wild claims get weeded out. With 3IATLAS, the early signs looked good for this careful strategy. The comet seemed to be behaving. It was interstellar, which made it exciting, but it wasn't doing anything that defied explanation. The spectra lined up with what you'd expect from a comet. The brightness changes made sense, probably just the comet's distance from the sun and maybe its rotation. The orbit was hyperbolic, sure, but each new observation tightened up the numbers, and everything fit with gravity doing its thing. No big surprises. Scientists got to work on papers. Drafts flew back and forth, analyzing the first observations, estimating stuff like how big the nucleus was, how fast it spun, and what all this meant for our understanding of interstellar comets. The story that was coming together, interstellar objects, at least some of them, aren't that different from the comets we know. They form in other star systems, but the same basic physics applies. No need to invent anything wild to explain them. It was a reassuring thought. It meant that everything astronomers had learned about comets and planet formation in our own solar system actually works elsewhere too. Interstellar visitors weren't totally alien. They were just new examples of a familiar story. But then ALMA stepped in, and the story took a sharp turn. The Atacama Large Millimeter Array, ALMA, sits high up on the Chajnantor Plateau in northern Chile, 5,000 meters above sea level. It's a powerhouse, built to pick up faint radio signals at millimeter and submillimeter wavelengths. That makes it perfect for studying cold gas and dust, star-forming clouds, the disks around baby stars where planets are coming together, and even the weak glow from distant galaxies. ALMA isn't just good at spotting molecules in comets, it's kind of a specialist. Water vapor, carbon monoxide, carbon dioxide, methanol, formaldehyde. Each of these has its own unique fingerprint at millimeter wavelengths. When you point ALMA at a comet, you don't just see what's there. You can actually measure how much of each molecule you're getting, see where they are in the coma, and watch how things shift as the comet spins or wakes up in patches. The whole array acts together as one instrument. 66 dishes, scattered across that high mountain plateau, all grab radio waves at the same time. Then with interferometry, ALMA takes the tiny differences in signal arrival times and pieces together a picture with way more detail than any single dish could ever manage. The end result: sensitivity and sharpness that nothing else in its wavelength range can match. So a team put in a request to use ALMA on 3IATLAS. Their plan: measure the molecular emissions and figure out what the comet's made of. They got the green light, and the slot lined up for a time when the comet was still pretty far from the sun, about 16 astronomical units out. Now at 16 AU, all the models agree. The comet should be dead quiet. Water ice doesn't sublimate out there. Carbon dioxide, maybe the faintest hint of activity, but only if the surface is weirdly dark and soaks up sunlight like crazy. Even then, that's a stretch. Most comets at that distance are just cold, dark rocks barely reflecting any sunlight. You can track them as moving points of light, but you don't expect to see any signs of gas or activity. The team aimed ALMA at 3IATLAS and started collecting data. They ran it through the analysis pipeline, calibrating, cleaning up, digging out the spectral lines from the noise. And then something turned up that no one expected: carbon monoxide. Not just a hint either, a solid, clear detection way above the noise. The 230 GHz line, a classic signature in cold space environments, was right there in the spectrum. They checked it again and again with different data. It was real. Suddenly, this wasn't the routine discovery everyone expected. The models didn't explain it. There was a real puzzle here. Finding carbon monoxide this far from the sun wasn't just surprising, it should have been impossible. At 16 AU, the sunlight is so weak that even the most volatile ices shouldn't be evaporating enough to create this kind of signal. Yet there it was. Hard evidence that 3IATLAS was alive, active, and measurable billions of miles from the sun. That one ALMA detection flipped the story. Papers about a typical interstellar comet had to be rewritten. New questions popped up everywhere about what the comet's made of, how it's built on the inside, maybe even about cosmic rays or other weird processes at work. Was 3IATLAS a good stand-in for other interstellar objects, or was it some kind of oddball? Other observatories with later slots closer to the sun suddenly had even more at stake. If the comet was already this active at 16 AU, what would happen as it moved in? Would it follow the usual patterns for supervolatile ices, or keep defying expectations? Would it ramp up its activity, or throw everyone another curveball? American scientists involved in the ALMA observations published their findings in peer-reviewed journals, carefully describing what was detected and what it implied. The papers were measured, technical, full of caveats about uncertainties and the need for follow-up observations. But beneath the careful academic language, there was a clear message. This object is not behaving the way we expected. We are observing something that challenges our models. We need to figure out why. And that's where the comfortable rhythm of expected discovery broke down. Because when nature hands you an observation that doesn't fit, you can't just ignore it. You have to engage with it. You have to test new hypotheses, consider alternative explanations, and be willing to revise your understanding. The scientific method demands it. But it's also uncomfortable. It's much easier to study objects that confirm what you already believe than to grapple with anomalies that suggest your models are incomplete. And 3IATLAS, by waking up 16 AU from the sun, had just become one of those uncomfortable anomalies. The detection wasn't ambiguous. It wasn't a marginal signal that could be dismissed as noise or instrumental error. It was a clear, unambiguous molecular emission from a comet at a distance where such emissions shouldn't exist according to standard models. The fact that multiple observation runs confirmed it, that independent teams verified the results, meant this was real. This was data that demanded explanation. And so the scientific community shifted gears, from expecting a straightforward interstellar comet study to grappling with an object that was breaking the rules in fundamental ways. The questions multiplied, the hypotheses proliferated, and the comfortable certainty of "we know how comets work" began to crack. Part 3. When the data refuses to behave. There's a weird feeling scientists get when data starts going off script. It's not panic, and it's not the thrill of discovery either. It's more like this cold, sharp focus. You double-check your calibrations, run the analysis again, dig through everything, hunting for errors or instrument glitches, any reason at all for why the numbers don't line up with what you expect. But if everything checks out, if the data holds up, then you have to face the real challenge, figuring out how what you see fits with what you thought you knew. That's where things started with ALMA's detection of carbon monoxide at 16 AU. It was just the first clue. Through late summer and into fall 2024, more and more telescopes turned their gaze on 3IATLAS. Every new observation filled in another piece of the puzzle, but the more we learned, the stranger things got. Then there was the James Webb Space Telescope. Its near-infrared spectrograph and mid-infrared instrument zeroed in on the comet's coma and immediately turned up something odd. Normally, in our solar system, comets are all about water. Water dominates, with carbon dioxide and carbon monoxide playing backup. The ratios are pretty predictable, tied to where and how the comet formed. But 3IATLAS didn't play by those rules. Its carbon dioxide to water ratio was sky-high, one of the highest ever seen in any comet. That points to two possibilities. Either the comet came from a place cold enough for carbon dioxide ice to stick around while water couldn't, or some process changed the chemistry of its surface, boosting carbon dioxide way beyond the usual. The Webb data was a technical triumph. Those infrared instruments pick up the glow from warm dust and the unique fingerprints of gases in the coma. Every molecule absorbs and emits light at its own set of wavelengths. Spread the light out, measure the peaks and dips, and you can tell exactly which molecules are there and how much. For 3IATLAS, Webb found strong carbon dioxide signals. Water was there, but faint. Carbon monoxide showed up in the infrared too, backing up the ALMA results. There were whispers of other chemicals, maybe methane, maybe ammonia, but those were right at the edge of what the instruments could detect. It would take more work to be sure. The dust measurements brought their own surprises. Optical and infrared telescopes picked up a steady continuum, a kind of light that comes from solid dust grains, not just gas. The amount of dust suggested that 3IATLAS was kicking up plenty of solid material along with the gas. Comets do this all the time, sure, but not at 16 AU. At that distance, you don't expect much gas at all, barely enough to see a coma, let alone carry dust away from the surface. The dust-to-gas ratio matters. It tells you what the nucleus is made of and how well sublimation, the process of turning ice straight into gas, is working. For 3IATLAS, the numbers said the nucleus wasn't just frozen stuff. It had a lot of rocky or carbon-rich material mixed in, and that solid stuff was escaping with the gas. That fits with what we call the dirty snowball model of comets. But seeing this much activity so far from the sun, that raises tough questions about how loosely the comet holds together and just how vigorous its outgassing really is. And then, as if things weren't strange enough, polarimetry entered the scene. When sunlight bounces off dust grains, it gets polarized, meaning the light waves line up in certain directions. By measuring that polarization, astronomers can figure out details about the dust, how big the grains are, what shape they have, even what they're made of. A team using ground-based telescopes in the US measured the polarization from 3IATLAS before it swung closest to the sun. The results were wild. The comet showed a negative polarization branch, a range of angles where the polarization flipped from what's normal, and did so more sharply and deeply than any comet or asteroid on record. The numbers sat way outside the usual range for solar system small bodies. So what's actually going on here? Basically, the dust or the surface of the nucleus, or maybe both, act nothing like what we've seen before. The way light bounces off this thing is just off. It doesn't fit what we know from all the comets and asteroids we've cataloged. Something about 3IATLAS is different, and it shows. Maybe the dust grains are weirdly small or way bigger than usual. Maybe they've got oddball shapes, think jagged, lumpy, or even wild, fractal structures. Or maybe the dust is made from stuff that reflects light in a totally different way, different levels of reflectivity, different ways it bends and scatters light. Each option points to a different underlying reason, but the takeaway is the same. 3I-ATLAS isn't your typical comet. And this wasn't a subtle thing. The polarimetric anomaly stood out. It was obvious, so much so that more than one group picked up on it independently. Some researchers think cosmic rays mess with the dust, changing its optical properties. Others wonder if drifting through interstellar space coats the grains in some weird way, building up thin layers that change how light scatters off them. As 3I-ATLAS moved closer to the Sun last October, people kept a close watch. Light curves from different observatories told a confusing story. The comet's brightness jumped around. It didn't just brighten smoothly, the way you'd expect from a spinning, evenly active comet. No, there were spikes, maybe outbursts, short, sharp bursts of activity where the coma flared up fast. Sure, comets sometimes explode with activity when a hidden pocket of gas bursts out, or a crack opens and lets stuff escape. That's nothing new. But with 3I-ATLAS, the timing and size of these brightening events didn't line up with what you'd expect from sunlight alone. A few of these flares popped up when the comet was still pretty far from the Sun, too far for heat to be the trigger. Some happened without any sign of new gases, which you'd usually spot in the spectrum if fresh material was venting. When you look at the light curves, they're a mess, peaks and dips, nothing regular or predictable. The coma didn't look symmetrical either. It suggested the nucleus wasn't active in a uniform way. A few folks even caught glimpses of jets or fans, streams of material shooting out from the nucleus. But the comet was distant and faint, so the images weren't exactly crystal clear. Then, October 2024 rolled around and the comet swung through perihelion, its closest approach to the Sun, about 1.4 AU. You'd expect things to get wild at that point. But for people watching from Earth, this was a tough moment. The comet was almost in line with the Sun, so ground-based coverage dropped off. Good thing we had spacecraft like Stereo watching from a different angle, picking up some of the slack. Honestly, perihelion is still a bit of a mystery because of that gap in observations. But once the comet moved out of solar conjunction and we could see it again, the story took a turn. It didn't break apart under the heat like a lot of active comets do. The nucleus stayed whole, but the coma changed. Observers started spotting new structures, maybe several jets or fans blasting away in different directions. Jets aren't rare. They form when parts of the nucleus heat up and vent gas and dust, spinning around like lighthouse beams as the comet rotates. Usually these jets look messy, fuzzy, scattered. Not this time. The jets from 3I-ATLAS held together, sharp and persistent, much more defined than the usual spray. Then came reports of antitails, those weird features that point toward the Sun, the opposite direction from the main tail. These can happen when solar radiation pushes dust grains of different sizes at different speeds. But with 3I-ATLAS, people weren't sure. The antitails looked odd, more structured and longer lasting than usual, enough to make even seasoned observers wonder if they were seeing just another antitail or something stranger. People tried to pin down how fast the comet's nucleus spins, but honestly, no one could agree. Some studies said it spun every few hours, which is pretty normal. Others pointed to a much slower spin, or even a kind of wobble, like the nucleus was lopsided and tumbling as it went around. This wasn't some random detail. How the comet spins changes how sunlight hits it, and that controls how it releases gas into space. If the nucleus turns slowly, one side bakes in the sunlight for ages and blasts out more gas from that hemisphere. If it spins fast, sunlight gets spread around and the gas comes off more evenly. But if the thing is tumbling, all bets are off. You get unpredictable bursts of activity, depending on which part faces the Sun at any given moment. Astronomers had another puzzle too. When they tracked the comet's path across the sky, something was off. If you account for the pull from the Sun and planets, you can predict where a comet should be. But comets rarely behave so simply. The jets of gas shooting off the nucleus act like tiny thrusters. They push the comet, nudging it off its expected course just a bit. You can actually measure this by comparing where the comet should be with where it actually is. For 3IATLAS, the extra push was bigger than you'd expect if only carbon monoxide ice was evaporating. Not outrageously big, it wasn't a weird case like Oumuamua, where the acceleration was so strange people started dreaming up wild theories. But it was enough to raise eyebrows. Maybe the comet was making more gas than expected, or maybe the jets lined up perfectly to give it a little extra shove, or maybe something else was going on. Scientists started building models. If the nucleus was small and super active, that could explain it. If several jets pointed in just the right direction, same deal. Maybe the outgassing was lopsided, pushing the comet harder in one direction. All these ideas made sense, but none of them fit perfectly with what we've seen from other comets. The problem was, each oddity had a possible explanation on its own. Weird chemistry. Maybe it came from a different star system with different ingredients. Activity farther from the sun than usual. Maybe it's loaded with ultravolatile ices, strange dust properties. Maybe its dust got baked by cosmic rays. The extra acceleration, lopsided jets. Sure, there's an answer for each mystery until you try to explain them all at once. If you used a composition model that matched the spectral data, it didn't fit the way the comet warmed up. The dust didn't behave the way the brightness measurements suggested. The amount of gas you'd need to explain the comet's push didn't match how much you actually saw coming off it. Nothing was wildly wrong, but the pieces just wouldn't snap together. There's this old rule in science, Occam's razor. Pick the simplest explanation that covers all the facts. That's the thing. Nothing about 3IATLAS was simple. Every theory needed extra tweaks, special circumstances, or just a bit of luck to line up with what astronomers actually saw. The comet wasn't breaking any laws of physics, but it seemed to be pushing them to their limits. Scientists at NASA Goddard, the Southwest Research Institute, and universities all over the country kept trying. They ran computer models of exotic ices boiling off. They worked out how cosmic rays might have changed the outer layers. They pictured a nucleus packed with hidden pockets or strange layers of ice and dust, or maybe gas trapped inside, waiting to burst out when the sun hit just the right spot. Some models nailed parts of the data. Others lined up with different observations but couldn't explain the whole story. Pretty quickly, it became obvious. No single neat explanation was going to fit all the weirdness. It took a blend of ideas, a lot of supervolatiles, maybe layers that had already been processed, possibly a strange shape or rotation, or those oddly active regions with their own quirks. This kind of patchwork isn't rare in science. Nature's messy. Every object carries its own backstory. Not everything slips neatly into our categories. Still, there's a line between this thing's complicated and needs a careful explanation, and this thing is acting in ways that just don't fit any of our basic models. 3IATLAS. It floated awkwardly in that gray area. Then there were the quieter observations, the ones you didn't find in journals. Just rumors, whispers in conference corridors, or buried in long email threads. Not bad data, just ambiguous stuff. The sort that's tricky to interpret and risky to trumpet without a pile of follow-up. Someone said they saw a forward-facing halo, a bright patch ahead of the comet that stuck around night after night. One way to explain it is dust getting shoved ahead by radiation pressure, but the angles looked off. Another group picked up brief, repeating flickers in brightness, maybe from spinning jets, except the timing didn't match any of the suggested spin rates. A third team thought they spotted fragments, little bits that might have broken off, but their equipment was pushed to its limits and no one else could confirm it. None of this crossed the line into rock-solid proof of something wild. These were all on the edge, uncertain, the kind of thing that makes you hungry for more telescope time, desperate to check if you really saw something or just caught a bit of random noise. Still, piece by piece, these odd observations piled up and the folks studying 3IATLAS started to get uneasy. It felt like the object was purposely dodging expectations. By late 2024, as the comet swung back out from the sun, heading for interstellar space again, the story was a mess. Sure, papers came out. Data got shown at conferences. Scientists tossed around models, but nobody really agreed. Some argued you could stretch existing ideas far enough, with the right assumptions to explain everything. Others looked at the pile of oddities and saw signs of something genuinely new, maybe about interstellar objects in general, maybe just about this one. The one thing everyone could nod along to: we needed more data. There was still time. The comet was bright enough for the big telescopes to keep watching, but it wouldn't last. Every week it faded and slipped farther away, harder to catch, longer exposures needed. In a few months, only the biggest telescopes could even spot it. After that, it'd be gone, vanishing back into the dark, secrets in tow. That's why the final weeks turned frantic. Teams scrambled for telescope slots. Proposals flew in. Observations happened fast, trying to catch any last-minute changes before the comet blinked out. People squeezed every bit of information they could from those last glimpses. Because if 3IATLAS was trying to tell us something about what interstellar comets are made of, or how cosmic rays change them, or just how much variety out there in the galaxy, we had this one shot to listen. Miss it, and we'd be left with half-finished stories, open questions, and the frustration of knowing we'd come so close to something big. That's just how astronomy works. You don't get to pick when these objects show up. You can't ask them to hang around a little longer. Nature calls the shots, and you scramble to keep up. Sometimes, you get clear, beautiful answers that fit right into your theories. Sometimes, you end up with a tangle of confusing data that just spawns more questions. 3IATLAS landed squarely in that second camp. Every new observation just tangled the story further. In the end, the community had to face a tough thought. Maybe our comet models, shaped by the objects here at home, just don't stretch far enough. Maybe interstellar space changes things in ways we don't get yet. Maybe there's a whole lot more variety, more surprises, out there in the galaxy than we ever expected. Or maybe 3IATLAS was just weird, an outlier, a cosmic fluke that happened to pass through our solar system during an era when we had telescopes good enough to notice how strange it was. In which case, the lesson was different. Don't overinterpret a single object. Wait for more examples. Build statistics. See if future interstellar visitors show similar anomalies or if 3IATLAS stands alone. But waiting is hard when the data is already in front of you, refusing to fit, demanding explanation. And that tension, between the desire to understand now and the intellectual honesty required to acknowledge uncertainty, is where science lives. In the messy middle, where observations and theory don't quite align, and the only way forward is more work, more patience, more careful thought. Part 4, The Silence of Science, and the limits of knowing. There's a certain hush that falls over a research group when the data stops making sense. It's not the sound of defeat, and it's not people giving up. It's that tense, thoughtful quiet, everyone staring at their screens, scribbling in notebooks, tearing apart their own ideas, and hoping they'll spot the one clue that makes everything fall into place. You'll find it in NASA conference rooms, in university labs all over the country, in long email threads bouncing across time zones. That's what happened to the teams working on 3IATLAS. It wasn't that they didn't have enough data. By early 2025, they were practically drowning in it: spectra, images, photometry, polarimetry, astrometry. Enough to write a stack of papers or keep a whole generation of grad students busy. No, the problem was what to make of it all. The observations kept poking holes in the existing models, never enough to break them outright, but enough to make everyone uneasy. Take the carbon monoxide detection at 16 AU. On paper, it checks out. Supervolatiles like CO can sublimate even far from the sun if you've got enough of it locked in the nucleus and the sunlight hits just the right patch. Feed those numbers into your model, tweak a few things, and the signal looks about right. But then you see a weirdly high carbon dioxide to water ratio, odd polarimetry results, dust showing up way farther out than expected, non-gravitational forces that are just a bit too strong. The coma keeps changing shape. Each one in isolation isn't too hard to explain, but try to fit them all together under one theory, and you end up elbow-deep in exceptions and just-so stories. The model that nails the CO emission flunks the dust production. The composition that matches your spectra doesn't line up with the polarimetry. You can force it all to work, but only if you assume a nucleus that's weirdly specific. This particular mix of stuff, this exact structure, this precise spin, this one-off history. And leaning on that kind of specificity just feels wrong. Occam's razor starts nagging at you. If you need a Rube Goldberg explanation to fit the facts, maybe you're missing something simple. Or maybe, just maybe, you've stumbled onto something truly odd that doesn't fit the usual boxes. This is the part of science that's more art than equation. You've got to walk that line between skepticism and imagination. Don't shoehorn the data into old ideas, but don't run wild with exotic theories before you've ruled out the basics. There's no cheat sheet for getting it right. So the 3IATLAS teams did what scientists do. They wrote up the results carefully, laid out the weird bits plainly, and tossed out possible explanations without pretending to have all the answers. You find words like may indicate, consistent with, suggests the possibility. Honest about what they know, clear about what they don't, and always asking for more data. Reading these papers, you can sense the tension beneath the measured prose. The authors know they're presenting something unusual. They know their colleagues will scrutinize every claim, every assumption. They know that publishing in peer-reviewed journals requires passing through a gauntlet of critical reviewers who will challenge anything that seems overreaching or insufficiently supported. So they're careful. They present multiple interpretations. They acknowledge competing hypotheses. They don't claim to have definitive answers. And in doing so, they uphold the standards of rigorous science, but they also leave the central mystery unresolved. Peer review process is demanding. When you submit a paper, it goes to an editor who selects 2 or 3 experts in the field to review it anonymously. Those reviewers read your work carefully, looking for flaws in logic, errors in analysis, alternative explanations you didn't consider. They write detailed reports, sometimes several pages long, pointing out weaknesses and suggesting improvements. The editor collects those reviews and decides whether the paper should be accepted, revised, or rejected. For papers on 3IATLAS, the reviews were thorough and sometimes critical. Reviewers asked hard questions. Why do you assume this particular composition? Have you considered this alternative explanation? Your data shows X, but you conclude Y. How do you justify that leap? The authors had to respond, often conducting additional analysis or softening their claims to address the reviewer's concerns. This process is frustrating but essential. It prevents bad science from getting published. It forces researchers to think carefully about their conclusions and to distinguish between what the data actually shows and what they want it to show. The result is papers that are more cautious, more hedged, but also more credible. Here's the thing, we don't always get clear answers, not right away. Sometimes you pile up observations, toss around theories, run a bunch of tests, and then just wait, sometimes for years, sometimes for decades, while more data trickles in and people start to agree. Other times, something shows up that just won't fit and it sits there unsolved, until maybe one day you spot another one like it and finally see the pattern. Take Oumuamua. Years have passed and people still argue about it. Some say it was just a weird comet or asteroid, something outside our usual experience. Others insist that its odd acceleration and lack of visible outgassing don't fit the basic comet story at all. The fight drags on because, honestly, we just don't have enough data. The object zipped by too fast, and our instruments weren't in the right place to catch the details. So now it hangs out in this gray area, halfway between a scientific mystery and a blank spot on our map. Now there's 3IATLAS. Maybe it'll end up the same way. We're bound to spot more interstellar visitors in the future. Some will look familiar, others will be completely bizarre. Over time, we'll start to notice patterns. Maybe we'll figure out which oddballs are just part of the usual cosmic mess and which ones really stand out. But right now, 3IATLAS is just one strange visitor. It's risky to draw any big conclusions from a single data point. There's a bigger idea here too. We live on a planet circling a pretty average star, in a galaxy packed with hundreds of billions of stars. Every one of those stars probably has its own planets, its own comets and rocks, its own unique story. thinking they all spit out objects just like ours. That's almost definitely wrong. The Milky Way must be bursting with variety. So when something from out there drifts into our solar system, it's not just a curiosity, it's a sample from the wider universe. It's a reminder that the cosmos is wilder and more diverse than anything we've seen at home. And if that sample doesn't fit our neat little categories, maybe the categories are the problem, not the object. No, this doesn't solve the mystery of 3IATLAS, but it helps put things in perspective. Science isn't about having all the answers lined up on a shelf. It's about stretching what we know bit by bit. Every time something doesn't fit, it's a chance to learn. That uncomfortable feeling you get when an anomaly pops up, that's not science failing. That's science doing its job, pointing out the edges of our knowledge. Astronomy's past is full of moments like this. Neptune got discovered because Uranus's orbit didn't make sense. We realized the universe is expanding because galaxies weren't acting like they belonged in a static universe. Dark matter came up because galaxies spun in ways that regular matter couldn't explain. Every time, scientists tried to squeeze the weird data into old theories. When that didn't work, they faced the music and admitted they needed new ideas, new physics, new discoveries. It wasn't tidy. People argued. It took time. But eventually, the evidence piled up and the whole way we understood things shifted. Maybe 3IATLAS is one of those turning points. Maybe not. It's still early. But the fact that it's making us rethink what we know about interstellar objects, cosmic rays, and planetary diversity, that has value, no matter how the story ends. American observatories played a central role in this process. The infrastructure built over decades, the telescopes, the instruments, the trained personnel, the funding structures that support long-term research, enabled the detailed study of 3IATLAS. NASA missions like Hubble and JWST contributed critical data. Ground-based facilities operated by universities and national labs filled in gaps, provided redundancy, allowed for continuous monitoring that no single telescope could achieve alone. This distributed, collaborative approach is how modern astronomy operates. No one institution, no one country, has a monopoly on discovery or understanding. Knowledge is built collectively, through shared data, open publication, and the free exchange of ideas. The team studying 3IATLAS included researchers from multiple nations, but the American contribution, both in terms of observational capability and theoretical modeling, was substantial and reflected decades of investment in scientific research. The National Science Foundation, NASA, the Department of Energy, these institutions fund the telescopes, the spacecraft, the research positions that make this work possible. Without that sustained support, we wouldn't have the capability to study objects like 3IATLAS when they appear. The investment pays off not in immediate, dramatic discoveries, but in the slow accumulation of knowledge that comes from studying thousands of objects over decades, building the baseline understanding that allows us to recognize when something genuinely unusual appears. But even with all that capability, with all that expertise, the central questions remain open. Why did 3IATLAS wake up so early? What does its composition tell us about the system where it formed? Is its behavior typical of interstellar comets, or is it an outlier? Can cosmic ray processing alone explain the anomalies, or is something else at play? You don't get easy, black and white answers with these questions. Scientists need more data, better models, and honestly, a few more interstellar objects to line up next to each other before they can really say what's going on. Until then, the people who spent months or years poring over this comet have to live with not knowing. They've added their own pieces to a puzzle with a lot of missing parts. They've nudged the boundaries of what we know, step by step. But they haven't landed that big, crystal-clear discovery that makes headlines or sweeps up awards. That's just how science usually goes. Most of it moves forward in tiny, uncertain steps. There are plenty of false starts, dead ends, and results that don't give you a clear answer one way or the other. Those big moments, The ones that change everything and get written into textbooks don't come around often. What's more common is the slow build, the gradual pileup of evidence that shifts people's thinking bit by bit, sometimes over decades. For the team working on 3IATLAS, there's this bittersweet sense of what might have been. If someone had spotted the comet even a few months sooner, they could have planned better, grabbed more telescope time, maybe even brought in special instruments. If it had taken a slightly different path, if it had swung by Earth a little closer or avoided the sun's glare, the data would have been much richer. And then there's the painful truth that this was a one-shot deal. 3IATLAS is gone, off into interstellar space, never to return. All the data anyone will ever get is what's already been collected. Sure, maybe future researchers will squeeze new insights out of that data, or invent new tools to dig up details everyone missed before. But nobody's getting a second look. The window slammed shut. This creates a weird relationship between scientists and the stuff they study. You chase something with everything you've got for months or years, and then, just like that, it's over. The object slips away, and you're left with whatever you managed to grab while it was around. No do-overs, no mulligans if you missed something the first time. It's a little like meeting a stranger who drops a life-changing idea in your lap, then disappears forever. You're left puzzling over what they said, trying to make sense of it, knowing you'll never get to ask a follow-up question or clear up what you didn't understand. The conversation's finished. All you've got are your notes and whatever you can remember. That's where we are with 3IATLAS. The comet's too faint now, too far away for any telescope to track. It's just another wanderer in the endless dark, lost to us unless it stumbles into another solar system millions of years from now. Whatever it showed us during its brief visit, that's it. Everything else is guesswork or modeling. Still, even with all the uncertainty and the gaps, this encounter mattered. It bumped up the list of known interstellar objects. It gave us data that'll shape how people think about how planets form and what comets are made of. It showed off some wild processes, supervolatile stuff vaporizing far from the sun, cosmic rays maybe leaving their mark, that push our understanding a little further. But maybe the most important thing is it reminded everyone that the universe doesn't care about making things simple for us. It doesn't hand us neat, tidy evidence that fits our models. Instead, it throws curveballs and mysteries, objects that just don't behave the way we expect. And our job isn't to force them into our old categories, but to stretch our thinking to fit what's really out there. That's tough work. It takes humility, the guts to say, I don't know, and actually mean it, while still pushing ahead, looking for answers. It takes patience, because real understanding creeps in slowly, with lots of people chipping away at the same problem from different directions, sometimes for years. The silence that settled over the research group studying 3IATLAS was not the silence of defeat. It was the silence of contemplation, the quiet between questions and answers, where the real work of science happens. The work of thinking carefully, challenging assumptions, and preparing for the next mystery that will inevitably appear in our telescopes, asking us to expand our understanding once again. Part 5, the question that remains. It's been several months now since 3IATLAS faded from view, dropping below the detection threshold of even our most sensitive instruments. The comet is still out there, of course, continuing its journey through the outer solar system and eventually back into the interstellar void. But for us, for the observers bound to Earth and its orbit around the sun, the object is gone. What remains is data, thousands of measurements, hundreds of images, spectra showing the chemical signatures of gases that shouldn't have been there, light curves tracking brightness variations that defy simple explanation. And what remains are questions. We're not totally in the dark here. We actually learned a lot from 3IATLAS. For one thing, it turned on way earlier than regular comet models would expect. Its makeup was weird too. Instead of being mostly water ice, it was packed with supervolatile ices. Polarimetry, off the charts, nothing like we've seen in other small bodies. Across every wavelength, all the way through its trip past the sun, it just didn't act like a normal comet. Not even close. But just knowing what 3IATLAS did isn't the same as knowing why it did it. And even if we crack the code for this one object, that doesn't mean we suddenly understand the whole population of interstellar wanderers, or what this means for how planets and systems form, or how stuff changes while drifting through the space between stars. The leading idea right now, the one that fits most of what we've seen without getting too wild, is cosmic ray processing. Picture this. For millions, maybe billions of years, 3IATLAS drifted through the interstellar medium, getting hammered by high-energy particles. Those cosmic rays break apart molecules, swap atoms around, cook up new compounds. Maybe simple ices like carbon monoxide turned into carbon dioxide. Water ice could have broken down or mixed into more complex organics. The surface might have gotten rougher, more porous, or formed a crust that's nothing like what's inside. If that's what happened, then interstellar objects aren't untouched samples from their home systems. They're changed along the way. Their journey becomes part of their story. To really understand them, we need to think about both where they came from and what happened during their endless drift through space. Honestly, this is thrilling for science. We can't just send a probe out to sample the cosmic ray soup directly, but we can study these objects that have soaked in it for ages. Each interstellar comet is like a messenger, carrying info about cosmic rays, the makeup of the space between stars, and how matter evolves over eons. Of course, that also makes things tricky. It's a lot harder to figure out what an interstellar object was like when it formed. You've got to separate what's original from what got changed along the way. It's a lot like piecing together what an ancient pot looked like when all you have is a weather-beaten shard that's been buried for millennia. The clues are there, but they're tangled up with everything that's happened since. The cosmic ray processing idea isn't just talk, it's testable. We'll find more interstellar objects in the future. If they show the same kinds of things, early activity from supervolatiles, weird makeup, odd polarimetry, then we're onto something. If every new object is a different sort of strange, maybe interstellar objects are just wildly diverse, and we can't lump them all together. That's the maddening part about studying rare things. You want patterns, you want enough examples to make sense of it all. But sometimes you just get a handful of oddballs, and you have to be careful not to jump to conclusions, because the next one could defy everything you thought you knew. Good news, help is on the way. The Vera Rubin Observatory down in Chile is almost ready. Soon, it'll start scanning the whole sky over and over, looking for anything that moves or changes. It's going to be amazing at spotting faint, fast-moving objects, including these interstellar visitors. Right now, the guess is it'll find several new ones every year once it's up and running. That's huge. Instead of a couple of lonely examples every decade, we'll have dozens, maybe even hundreds over the next 10 years. That's the kind of data we've been waiting for. And with those additional examples, we'll start to see patterns. We'll learn whether 3IATLAS was typical or unusual. We'll see if early activity at large distances is common for interstellar comets or rare. We'll build statistics on composition, on polarimetry, on outgassing rates. We'll develop a taxonomy of interstellar objects, classifying them into groups based on shared characteristics. There are alternative hypotheses, of course. Some researchers have suggested that 3IATLAS might have originated in a stellar system very different from ours, maybe one with a different ratio of elements, where carbon-rich ices naturally dominate over water. The composition we observed wouldn't then be the result of processing, but of original formation conditions. That's plausible, but it requires assuming that planet formation around other stars can produce radically different comet populations, which pushes into territory where we have very little empirical data. Others have speculated about internal heat sources. Could radioactive isotopes inside the nucleus provide enough warmth to drive sublimation at large distances? Could there be chemical reactions occurring in the interior, releasing energy? These ideas are harder to test without direct measurements of the nucleus's composition and structure, which we don't have and won't get unless a future mission actually visits an interstellar object. Then you've got the observers, the skywatchers, mostly amateurs but with a few pros, who look at those images and say, wait a second, 3IATLAS just looks too neat, too tidy for a regular comet. They'll go further, wondering if it's artificial, maybe a chunk of debris from some interstellar probe, or even a vessel with a purpose we can only guess at. To them, it's just too weird to be natural. Now, these ideas are way out there, and the mainstream scientists haven't seen anything to back them up. Nobody picked up any unusual signals. Spectroscopy didn't show anything you wouldn't expect from regular comet ice. Sure, the comet's accelerations were bigger than usual for something that far from the sun, but outgassing still explains it. Everything we saw, with a bit of stretching, fits under natural causes. Still, the fact that people are even asking these questions says something. 3IATLAS didn't act like the comets we're used to. It threw enough curveballs that even the wildest theories got a moment in the sun before getting tossed aside. Honestly, that's how science works best. You're supposed to keep an open mind, even for ideas that sound nuts, and then whittle them down with evidence and logic. The trouble starts when people hang onto the long shots after the facts have moved on, or twist what scientists are saying to make things look more mysterious than they really are. But that initial "what if?" that's not a problem. That's just curiosity doing its job. So where does that leave us now at the end of this story? We've got an interstellar comet that started acting up billions of miles from the sun, spewing carbon monoxide gas when it should have been frozen solid. It's got a weird makeup, strange optical quirks, and behavior that kept nudging the limits of what our models could handle, never quite breaking them, but definitely stretching them out. Scientists pounced on it while they could, grabbed all the data they could manage, floated explanations, and now they're waiting, hoping that something else from deep space will show up to fill in the blanks. And there's still this big, open question, not because we're missing something obvious, but because nature just doesn't hand out answers on our schedule. What does 3IATLAS actually tell us about the galaxy beyond our solar system? Is it normal? Are most interstellar objects this strange, and we just lucked out with a more typical one like Borisov before? Or did we just catch a real oddball this time? A statistical blip that happened to drift by while we were watching? Are the things that changed it, cosmic rays, wild temperature swings as it bounced between stars, collisions or near misses with other space junk, just part of the usual routine for anything drifting between stars? And if they are, what does that mean for all the small stuff floating through the galaxy, for how organic molecules and ices get scattered from star to star, for those big picture ideas about life's building blocks getting seeded across the cosmos? Those aren't just throwaway questions. They cut right to the heart of how we see the universe and our spot in the middle of it. If interstellar objects are common, if they're always moving and carrying altered materials between star systems, then the galaxy is way more connected, dynamic, and chemically blended than we thought. Matter doesn't just stick where it started. It breaks free, drifts, gets caught by another star, or just keeps wandering in the dark forever. Picture the Milky Way as a living, sprawling ecosystem, stuff and information darting around, following the paths gravity lays out, sometimes just colliding by luck. Our solar system isn't some walled-off fortress. It's been getting visitors and hand-me-downs from the wider galaxy since it formed. Makes you stop and wonder, how many interstellar objects have smacked into Earth over billions of years, dropping off ices, organic materials, maybe even the first ingredients for life? Then again, maybe 3IATLAS is just a weirdo, and most interstellar guests are pretty dull. Maybe the galaxy's packed with wild planetary systems, all flinging out their own weird comets, and we just happen to spot one of the oddballs this time. If that's the case, the lesson changes. Don't read too much into a single discovery. Be patient, keep watching, gather more data. But even if 3IATLAS really is an outlier, the encounter still shifted things for us. It made us think bigger. Suddenly, there was something new to see, something that didn't fit neatly into our old ideas. It nudged us to question what we thought we knew, to sharpen our models, to get ready for the next surprise. Another interstellar object will show up. No clue when or what it'll look like, but our surveys keep getting better. We're catching more. Soon, finding these visitors won't be rare, it'll become routine. When it happens, we'll be ready. 3IATLAS taught us what to look for, like supervolatile gases showing up far from the sun or strange pushes that don't follow gravity. We'll check the light more carefully. We'll analyze spectra top to bottom. This time we'll be thorough. Maybe the next visitor will fit right into our models. That'd be nice, comforting, even proof that the universe makes sense. Or maybe it'll be even stranger and we'll have to rethink everything. That's the deal when you're exploring the unknown. You never know what's coming next, but you keep searching. You keep pointing telescopes at the sky, crunching numbers, asking questions, poking at your own assumptions. That's how knowledge grows, one observation at a time. 3IATLAS is gone now, off into the dark it came from. But it left a mark, a heap of data, a mess of new questions, and a reminder that the universe is packed with wonders we haven't even dreamed of yet. Sometimes, if we're lucky, one of those wonders passes close enough for us to catch a glimpse. Next time you look up at the stars, remember, out there, past what our telescopes can see, objects are drifting between suns. Some are ancient, leftovers from stars that died eons ago. Others are young, fresh from newborn systems. Each one carries a story, a history written in its makeup and the way it behaves under a new star's light. We're only just starting to decipher those stories. 3IATLAS was just one chapter. More will come. With every new visitor, every new bit of data, we'll figure out a little more about our galaxy, about how matter moves and changes across time, about the invisible web connecting stars and worlds. The real question isn't whether we'll solve these mysteries. We will, eventually. The real question is what we'll stumble across along the way. What oddities will force us to change our minds? What new kinds of objects will we need to invent names for? That's what makes the search worth it. Science doesn't promise easy answers or quick resolution. It promises only that if we keep looking, keep questioning, keep testing our ideas against reality, we'll inch closer to truth. Sometimes that truth is uncomfortable. Sometimes it's beautiful. Often it's both. 3IATLAS woke up 16 astronomical units from the sun, billions of miles too early, according to everything we thought we knew. And in doing so, it whispered a truth that the universe has been trying to tell us for centuries. Your models are not complete. Your understanding is not final. There is always more to learn. Listen to that whisper. It's the sound of the cosmos inviting you to keep exploring, to stay curious, to never assume you've figured it all out. Because the next mystery is already on its way, traveling through the darkness, waiting for the moment when it crosses into the light and asks us, once again, to expand our understanding of what is possible. The silence between stars is not empty. It's filled with wanderers, with messengers, with objects that carry the history of places we'll never visit, times we'll never witness, processes we're only beginning to comprehend. And every so often, one of those wanderers passes close enough for us to see, close enough to study, close enough to challenge everything we thought we knew. 3IATLAS was one of those wanderers, and though it's gone now, vanished back into the interstellar night, its message remains. A whisper in the data, a question in the models, a reminder that the universe is stranger, more complex, and more wonderful than we dare imagine. And that whisper asks us, are you ready for what comes next?